gamma spectroscopy a little bit, and well, I'm gonna rewind a little bit and go back to like Compton scattering. So the three, remember the three different ways that photons or gammas can interact with matter is, what are the three ways?
Compton scattering.
And pair production. And Compton scattering is when a photon interacts with an inner shell electron.
No. Outer
Yes.
shell.
Outer shell. So which one is the one where photon interacts with an inner shell? Photoelectric effect. And so photoelectric effect, that photon is giving all of its energy to that electron, right? So if we look at a gamma spectrum, that means that that would correspond to what on a gamma spectrum? What is it called? Remember you have like a peak right here. This is something, this is something, that is that. You need to be able to, so if I'm looking at a gamma spectrum and I want to know what energy corresponds to the photoelectric effect.
The tall one at the end.
Yes, what is this called?
The photo peak.
Photo peak, right, photo peak. What other peak on here corresponds to the photoelectric effect?
The first one, but I don't remember what it's called.
So what happens when your electron is given all of its energy, the photon gives all of its energy to an electron, it can get ejected from the atom, right? So what happens with that space? Another electron drops down, emitting a what?
OJ.
No.
X-ray.
X-ray.
And then
So
the X-ray
this is
goes
an
over
X-ray.
to OJ.
So those are photoelectric effect. Those are photoelectric effect peaks. So the other ones are associated with, what's the other one? Compton scattering. So when we're looking at Compton scattering, remember you have your photon or your gamma coming in. It's gonna eject this electron. So that's electron with a little, what is that thing called? Postry or whatever, or primary, whatever. And then the photon will get scattered at some angle theta, right? So, or it could get scattered all the way back this way. So you could have scattered all the way back this way on this angle. So what this represents is all of the energies of this photon, the scattered photon, okay? So this would be the Compton continuum. Sounds like a rap group. All right. Right. All right, so what does this peak, what is that peak called and what does that represent?
That's, wait, which one? Is that not the Bragg's peak? Or that's the Compton edge?
Yes, this is the Compton edge.
I don't know.
And what does that represent?
Compton scattering?
Yes.
I don't remember.
So at some point, the angle that the photon interacts with the electron will transfer like the maximum amount of energy. And there's also an angle where it will produce the minimum amount of energy, which would be a backscatter peak. So a backscatter peak, actually no, that's not a backscatter. A backscatter peak is what happens when you have a photon. So here's your detector. It can be your eyeball, it can be your skin, whatever. So you have some sort of photon that's interacted with matter, and now you have maybe this photon reaches, that the scattered photon reaches the detector, which would be represented here, okay? However, comma, this scattered photon could not go into the detector, right? But it could also interact via Compton scattering and get back scattered back into the detector, okay? So this is what this is. This is a backscatter peak. Okay? So the reason why the Compton continuum is so long is because at the different angles that they're scattered, they have different energies. So if you remember the equation for a scattered photon and a Compton electron, so the total energy, which is represented by your photo peak, so we'll just say total energy, or you can say E sub naught, either way you write it, is equal to the energy of your Compton electron plus the energy of your scattered photon. So if you take the energy that started here and the energy of this and the energy of this, they should be equal, okay? So conservation of energy. Now, how do we calculate what happens to the energy of the scattered photon and the energy of the Compton electron? We have two different equations. One is pretty easy, the other one, you can do it like this if you want to. So we have the energy of the scattered photon, and you'll be provided these equations, but just so we can remember how to calculate it. I don't have it memorized either. So you have your initial energy divided by 1 plus, and this does not have a unit, okay? So a lot of, there's a couple folks on the homework assignment that would assign MEV here. This does not have a unit, okay? So it's just E sub naught, or the initial energy, divided by 0.511 times 1 minus the cosine of theta, okay? Depending on theta, the angle of theta, it will determine what the energy of that scattered photon is. Now, if you want to figure out the energy of your Compton electron, you can just take your total energy and subtract that from your scattered photon energy, and you get your Compton electron energy, okay? And those should equal up. So, if you're, definitely will be asked this, to label these parts and maybe tell me which peaks belong to which property of the photon or gamma interaction, okay? So which gamma interaction on this graph represents the photoelectric effect, you would label those. Which ones correspond to Compton scattering, you would label those. Now, if we want to talk about pair production, that graph's going to look a little different, but we also have to know that the minimum energy for pair production to take place is what? 1.02 to MeV, right? So if you're given something and some sort of reaction, and true or false, the energy of this reaction, this reaction is happening via pair production, and the total energy of the reaction is 1.0 MeV. It would be false, because it's no way it can happen. It has to be at least 1.02. Also, if you're given a decay diagram, and you are to determine whether or not it's electron capture, or pair production, or beta plus, it has to at least be 1.02 MeV to be positron decay or pair production, okay? Because pair production produces a positron and it produces a negatron, an electron, okay? So the energy of both of those is 0.511 MeV. Add them together, you have to have at least 1.02 MeV in order for pair production to take place and for positron decay to take place, okay? So there will be, just make sure you remember that. All right. Spectrophotometry. So kind of moving away from gamma spectrum, moving to spectrophotometry, knowing the parts of a spectrophotometer, just being able to like label, point to the monochromator, or what does the monochromator do? So being able to label those parts. And then what things can be determined from a UV vis spectrum? What things do we do in lab using the UV vis?
Say that one more time.
What things did we do in lab? So when we were doing, using the UV vis, what kind of experiments were we doing? What were we trying to determine?
That was with the lanthanides.
Yeah.
Concentration.
Concentration, yes. What else can you determine with the spectrophotometer? What'd you say? Yeah, absorbance. And transmittance. So knowing the relationship between absorbance and transmittance. They're somewhat inversely proportional, and knowing that the colors that we see are the colors that are transmitted. So when we're looking at a spectrophotometer, we're looking at absorbance measurements, because a spectrophotometer, the transmission is what we're seeing with our eyes. It can't read the it can't read transmission, but it converts it from an absorbance measurement. You can also determine reflectance properties of the surface and chemical reactions, things like that. So if we were able to do it this year, if we were looking at a flow cell, if we had a flow cell, and I know we talked about like what a flow cell looks like and how it works. You basically have a cuvette, it's got an entrance and an exit, and you connect tubing to it, and you can pump material through it, and you can watch on a spectrophotometer in real time what is happening as things are coming off your column. So if you had a mixture of your lanthanides, you have neodymium, praseodymium, and what was the samarium? They all had different colors, right? Well, if you have a mixture of them and you put them on a column and they have different distribution coefficients, determining how to get them, selectively isolate them and strip them off your column so that you can see them on a spectrophotometer. That is a way that we can combine several different processes all in one. So you're able to determine like what's going on with a chemical process. So what's coming off your column based on what KD values associated with each of those lanthanides for whatever resin that you're looking at or solvent extraction process. Let's see. Okay, yeah, I just went over that. All right, and then the Beer-Lambert law. I think we had a mnemonic for that, not a mnemonic, but a way to memorize which one is the Lambert law and which one is Beer's law. So Beer-Lambert law, I'll make a marker. And that's broken. I love it. So our Beer-Lambert. Says absorbance is directly proportional to the molar absorptivity or molar extinction coefficient times the path length times the concentration. So if you have a high concentration, your absorbance number will be high. Absorbance numbers are unitless, so it is not going to mean anything. Your path length is usually given in centimeters, and your molar absorptivity constant is usually given in inverse moles, inverse centimeters. So we can cancel out these two things. All right. So if I have something that's very, very concentrated, do I need a short or a long path length? What? Very, very concentrated?
Yeah, long.
Are you sure?
If you want something very concentrated?
Now, if I have something that's very concentrated and I want to read it on a spectrophotometer, this is constant, this is constant, this is a very high number, so what would you want your path length?
I guess
You want a short path length, right? Okay, so if we're looking at like vector analysis here, this is going up, this is going down, so they cancel each other out, so it would be constant. These two are constant, so constant and constant. That's how you kind of work that out. If you have a very dilute solution, the opposite is true. If it's very dilute, you want a very long path length so that you can get an absorbance value, okay? Yeah, that kind of sucks. Let's see.
Neighbors like running up my chickens right now.
All right, so Lambert's law states the relationship between the absorbed light and the thickness of the medium. Is that true or false?
True.
False.
Okay, Lambert's law states the relationship between the absorbed light, the absorbance, and the thickness. Yes, that is Lambert. Okay, so Lambert, length, L,
Okay.
right? And then Beer's law is C. I don't know what we want to relate to beer with, maybe Coors. I don't know. I don't drink it. So just knowing the difference between, that'll probably be like a true false type of question, just so we know which part of the law we are looking at. I might delete this question because it's too easy. That one's also too easy. Okay. If you are, let's say you are given a KD value table. So remember when we're looking at distribution coefficients, and this is on the last homework too, about what the distribution coefficient, what does that tell you? It's basically how well your stationary phase or your organic phase will attract or keep a certain radionuclide. So when you're looking at a table, it usually looks like a periodic table, but on each square, you'll have an acid concentration. Let's say we're in nitric acid, and then you have your distribution coefficient on the side, okay? And this is usually the log. All right, let's say we're looking at two different lanthanides, and I want to separate them, okay? So one lanthanide at low, let's say a low nitric acid, yes?
You said a stationary phase?
Yeah, so your stationary phase compared to your mobile phase. So, or your organic phase concentration over your aqueous. So if we're looking at KD, we're looking at the concentration of the organic phase divided by the concentration in your aqueous phase. Or it could be looked at as the amount retained in your stationary phase divided by the amount retained in your mobile phase. Okay, because if we're looking at a resin, okay, you've got a column, you got stuff coming out, right? We want to know, like, there's your resin, it's cross-linked, whatever. We want to know how well this resin keeps this lanthanide on here. So how much it can retain on the stationary phase versus how much is actually getting out, okay? So how well something sticks, right, is your KD value, or how well something is retained in the, or extracted into the organic phase. So if I'm looking at two different lanthanides and I want to know, like, what's the best method for separating them? In order for us to adequately separate something, the KD value for one of the species needs to be either really high or low, and then the opposite is true for the other species. So at a very low nitric acid concentration, we'll say species 1 has a very high KD value. Okay, and this is usually, it'll look different for each lanthanide, right? Then we want to look at our other lanthanide that's in our mixture, and we want to determine, okay, what's the best way to separate it? And there, this particular KD value curve looks like that, okay? So if I want to separate these two, I would, if I'm loading it on a column, or if I'm using some sort of solvent extraction process, I want to use a nitric acid concentration that is very low so that the lanthanide does not stick. So this KD, that it does stick. So I want to use a nitric acid concentration that's low because the KD value for this one is very high. So that means it's going to stay on my column, okay? Now, if I use that same nitric acid concentration, so I'm looking like right here, same nitric acid concentration, our KD value is lower here. So we might have a little bit stick, but the majority of it will come off, okay? Now you can do it in reverse. You can load in a very high nitric acid concentration right here, however, comma, it looks like your KD values are gonna be very close, so you might not get a very good separation, okay? So that's why KD values are very, very important when you're doing solvent extraction or like resin column separations, knowing how well something is gonna stay on a column or how well something is gonna extract into the organic phase. So you may be given a scenario where you're given a couple of KD values for different lanthanides, and you will have to explain your method for separating them, okay? So I would load, or I would start with dilute nitric acid or hydrochloric acid, and then to isolate this lanthanide. Then I would switch to this concentration of nitric or hydrochloric acid to isolate this lanthanide, so forth and so on. So that's the kind of answer I'm looking for on a question like that, okay? Let's see. Oh, yeah, keep going. All right, so reactor production, accelerator production, and cyclotron production of radionuclides. Remember that accelerators and cyclotrons are normally for charged particles. So they are going to make beams of charged particles that will make your radionuclide of interest, right? So if you are looking at, let's see, you're given this. Or, let's see. You're asked which one of these reactions can happen in a reactor. Which one would you pick? Can you see that?
The one with the neutron?
Okay. That's a good answer. Which one of these reactions happens in a reactor, a nuclear reactor?
I guess the first one.
Yeah, the first one, but all of them do.
Oh, it was a trick question.
Reactors, you get neutrons, you're producing everything in there, right? So reactors can produce everything in there. But if you are looking for large quantities of material, reactors can make small and large quantities of material. But normally, reactors can produce almost anything. Now, if you're looking at producing something very specialized and you're looking for a very specific reaction that involves a charged particle, then you want to use an accelerator or a cyclotron, okay? Now, if we want to determine what the yield would be for our specific irradiation scenario, like I have 5 grams of neptunium-237 and I want to irradiate it for 5 minutes, and I have the flux, and I know the cross-section, then I can determine how many atoms of neptunium-238 I'm going to make, okay? So we'll work through that really quickly. And this is on the last homework too.
I think that was the one that all of us got slacking on.
Yeah, and I have to go back and check the math on that because I was getting, the answer was right until like the last part when you added in the multiplied by the 1 minus e to the negative something or other, lambda t. So I had to go back over it because I was looking at it this morning. I was like, gosh, I feel like
For homework
something is wrong
4?
with the math there. All right, so we'll go over that in a second. So if we want to calculate yield, we want to know how many atoms that we're producing of whatever we're trying to make. So for this instance, I have neptunium-237, and I want to make neptunium-238. All right, how are we going to make neptunium-238 from neptunium-237?
Neutron.
A neutron, right? So I need a neutron. So what's going to happen to this neptunium-238? It's going to have some gammas associated with it, okay? So if we want to write this shorthand, we have that's that's how that would look. That's how that whole reaction would look. It would be called an N-gamma reaction. So if we want to determine how much of this we're going to make, so this would be N sub B. There are a couple things I need to know first. I need to know what my flux is gonna be. Okay, so flux is usually given in neutrons per centimeter squared second. I also need to know my cross section, what is a cross section? Yes?
What is the flux?
Flux is, okay, so in the definition, it's telling us how many neutrons. So if we have a square centimeter of space, okay? And obviously, there's way more space than that, more area. If I have a square centimeter of space, and I want to know in this space, in this little square centimeter, this area, how many neutrons are passing through per second. Okay, so these are neutrons. How many of these neutrons are passing through this little square centimeter of space per second? So your flux is that number. So there's millions and millions of neutrons out there. Normally, flux is going to be somewhere around, if I'm thinking about high flux isotope reactor, the flux is usually 2.1 times 10 to the 15th neutrons per centimeter squared per second. So per second, per square centimeter, I have 2.1 times 10 to the 15 neutrons passing through that little square centimeter of space. Okay?
So it's just how many neutrons the reactor can shoot at the.
Yeah, in a square centimeter space. So obviously, if you have a large nuclear reactor, you have multiple square centimeters. But if we are looking at the total amount of neutrons being produced, that's a different equation. But normally we deal with flux so that we know what it is per square centimeter area. And then there's other factors that we put in there to determine, like the thickness of our target, the shape of our target. Usually there's a computer code called MCMP. It's Monte Carlo end particle code that allows you to determine like how many of these you're going to make. So MCMP is like a more fancy version of this, but this is a very simplified version. So our flux, what is our cross section? What is our cross section telling us?
It's the probability of interaction.
Yes, the probability of interaction, and it's given in units of
Barnes.
barns. But what the hell is a barn? That doesn't fit in here. What is a barn equal to?
10 to the negative 24 centimeters squared.
Yes, so barn is equal 10 to the minus 24 centimeters squared. All right, so we can see how these will cancel out. So what else do we need to know in order to determine how much of this we're gonna make with this starting material?
Lambda.
We need to know how much of this we have,
Oh.
right? Oops. So this would be our N sub A, which is not Avogadro's number. We know we're weirdos, we like the same numbers here. So I need to know how many atoms of this that I'm going to be irradiating with this probability of interaction, with this amount of neutrons per centimeter squared area. And then I need to know something else, like what else do I need to know here?
Lambda? Maybe? I know lambda's in there somewhere.
Let's look at unit analysis. What do we have left? Seconds. So I need to know, like, how long am I gonna be irradiating this? So I need time, okay? Usually in seconds, days, whatever. So those will cross out. So now you're gonna be left with neutrons per centimeter squared second times centimeter squared second times seconds. So usually you end up with something like atoms here, okay? Now if you know the molar mass of the Neptunium-237, you can determine how many grams you're gonna make, okay? So if you're working through a problem like this, and you want to know how many atoms of Neptunium-238 I'm gonna make if I'm giving X amount of grams of Neptunium-237 and I irradiate it under these conditions, this is how much I'm gonna make. However, is this stable? No, okay. So if your product, what you're making, is also decaying too, Now what do we have to do?
1 minus.
We have to account for its decay. So we have our normal production equation times 1 minus e to the minus lambda t, all divided by lambda. Now, if you want to rearrange this equation, you can see that lambda n, what does lambda n tell us? Activity, right? Yep.
On your slides, it does not have the T in the numerator.
In this part?
Yeah.
Oh, for this part?
Yeah.
Yeah. All right, so we are looking at production of our Neptunium-237, but it's also decaying. So you want to account for how many atoms are decaying per unit time, okay? Rearranging it just to get the number of atoms, so we divide by lambda, and we also account for its exponential decay with the 1 minus e to the lambda t. 1 minus e to the negative lambda t. All right. Any questions on that? There will be yep.
Will we still need to factor in time even though it's not in the equation? Or?
Yeah, time will be in here.
Okay.
Yeah, because you still need to know like how long since it's created and it's being decayed. Because as it's being created, it's decaying at the same time. And that does kind of tie into our production and decay terms. If you guys remember branch decay. So if you guys remember how those equations are set up, it's very similar to that. Except for you're inducing the actual production instead of it just decaying into something. All right. Okay, do we remember the terms exoergic and endoergic? Okay, if you have a Q value that is negative, what is that telling us if your Q value is negative?
Endo?
Yes, it is saying that. It's endoergic, but what does endoergic mean? Because, huh? An endoergic reaction is not spontaneous.
Right, how? How?
Huh? So if your Q value is negative and it's not spontaneous, do I need to give it energy to move it forward?
Yes.
Yes, okay. So an endoergic reaction or a Q value that is negative means that you have to give that reaction energy in order to move it forward. If your Q value is positive, it can be spontaneous, it can be a spontaneous reaction, and it would be considered exoergic because energy is being released, okay? So if you have to supply energy to the reaction, it's gonna be endoergic, or the Q value is negative, okay? So you might have a situation where you are calculating the Q value for a reaction, and the Q value is negative. Then you have all sorts of other lovely, wonderful equations you would have to use, like threshold energy, Coulomb barrier, effective Coulomb barrier, or it could be something as simple as calculate the Q value and tell me whether this reaction is endoergic or exoergic, okay? So remember, endo, negative Q value. I don't know how to relate that to each other.
Endo has an N in it. Negative.
Okay, well, there you go. So, there you go. So endoergic, exoergic reactions.
Endo has an N in it, so it's negative.
Also, speaking of negative Q values and the other equations that we would have to calculate, like threshold energy and the Coulomb barrier and the effective Coulomb barrier, knowing which particles are actually going to experience those things. So if I'm asking a question like, will this particular reaction, let me write this one down. Actually, I can use this one. I'll just erase all this other stuff. I'll just rewrite it. So that's Neptunium-237. And I asked you to calculate the effective Coulomb barrier for this reaction. Will you be able to calculate that?
Just given that?
Yeah, if I ask you to calculate if I give you values, right?
Mhm.
And ask you to calculate the effective Coulomb barrier with this reaction, will you be able to calculate that?
I think so.
Are you sure? So what is, okay, let's think about this. Coulomb barrier, Coulombic repulsion. What is Coulombic repulsion doing?
It's a neutron.
It's
Okay,
a,
it's a neutron. No,
oh.
I will not be able to calculate Coulomb barrier for this because it doesn't experience Coulombic repulsion.
Yeah.
Tricky, right? So it doesn't experience Coulombic repulsion because it's neutral. Only things that will experience Coulombic repulsion are charged particles. So if this was in alpha, so that means this will change to 1. Alpha, no, be alpha. Wait, no. Yeah, I'll just do alpha, even though that might not be an actual reaction. So if I asked you to calculate the effective Coulomb barrier or determine whether or not this reaction would experience Coulombic repulsion, then yes, this would, because an alpha particle is normally a charged particle, usually has a +2 charge if it's stripped of its electrons, or if it was like a deuteron or a proton or anything that's got a charge, it will experience some sort of Coulombic repulsion. So if you have a neutron up there, and I give you all these numbers, and I ask you to calculate the effective Coulomb barrier or something like that, you know, and you start plugging away numbers, please just slap yourself. Don't do it. Don't do it, don't do it, because the neutron will not experience Coulombic repulsion. So you may see something like that, little tricky questions like that. Just think back to what am I actually asking? Coulombic repulsion is, you know, you got a positively charged nucleus. Anything that's got a positive charge is going to be repelled by it, okay? Yeah, it leads me into that question. Okay, yeah, and then calculating cross sections. So basically you're just rearranging if you're asked to find the cross-section given a reaction and you have all of the other terms, all you gotta do is rearrange the equation, solve for cross-section. Please make sure you use the units. It will only help you, okay? Units, 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 because you get lost in the sauce and then you end up calculating things that are incorrect. Or if you have things in meters or grams and you need millimeters or milligrams, just use your units, make sure that you're keeping everything correct. Okay, the expected yield, we already did that.
Keep it in the box, not outside.
Huh?
Keep it in the box of observation, not outside of the box.
Yeah, don't answer the question asked. Yeah, do not answer the question that is not asked, because then you're just gonna get it wrong. Okay, knowing the parts of the cyclotron, how a cyclotron operates. Okay, so remember we have, over here. So cyclotron, you start with some sort of ion source. So you have a little ion source here. And it's producing charged particles, right? So remember, cyclotrons and accelerators, charged particles, reactors produce everything, okay? So you have a little ion source. Let's see if I can get my picture right. Y'all love my drawings here. And we have a magnet here, and we have a magnet here. And then we have what's called the D's. So we get two D's.
We got two of these.
Two of these.
We got two of these.
We got two of these, right? Okay. And then you have some sort of, something like this. Okay. I'm probably drawing that a little bit incorrectly. I mean, do it like that.
Is that based off, is that static electricity? Are you like using that right there?
I did not hear you.
It's a static electricity. Is that what these are?
No, this is alternating the voltage.
Oh, okay. It
Yeah.
looks like one of those huge electrode, you know what I'm talking about? Those electrode.
No, I don't.
Okay.
I'm sorry, yeah, but the Ds are part, so this is all inside of like a housing. This is all inside of a housing. We're doing a cyclotron. All right, so you start with your ion source, and this ion source is going to travel, it's going to be attracted to one of the Ds. So let's say this is a positive ion, right? It's going to be attracted to this D, which will have a negative charge, okay? So it'll be pulled this way towards the D. However, the magnets will have a force as well that are going up and down, right? So your magnetic force is going this way, your ion force, or whatever is it, I forgot the name of the force. Remind me to look that up, is going this way. So now you're going to experience what's called a Lorentz force, which is going to go diagonal. So it's that right-hand rule, right? So if you have your electromagnetic force going this way, and you have another force going perpendicular to it, you'll experience a Lorentz force which will cause it to turn, okay? So your positive ion source is going to be drawn to your D, which temporarily is going to be negative. So it's going to travel, it's going to be bent by this Lorentz force, and as it skips over this barrier here, it's still gonna be positively charged, right? Well, if this is negative and that's positive, this is gonna repel it. So as the ion reaches the gap between the Ds, the charge will flip, okay? So now it's drawn towards this D, and will experience that same Lorentz force, which will cause it to go in a circle. So as it goes around in a circle, it obviously isn't this wide. It'll start out small, and then it'll get larger as it's traveling around. It speeds up and it gains energy, okay? So the important thing about cyclotrons and accelerators is that at certain energies of your charged particle, you can induce certain reactions, okay? Kind of like how Q value needs, a negative Q value needs a certain amount of energy to move the reaction forward. So your proton or your electron or whatever kind of ion source you have in there, your deuteron, needs to reach a certain energy in order to induce a reaction in your target. So as this thing is traveling around, eventually it's gonna make it out. So I'll just draw a little tube here. Eventually it's gonna make it out to your target. Okay, and it's gonna have some energy. Your target is gonna be made of, it can be a solid, it can be a liquid, it can be a gas. Most of the time it's a solid, and usually it is a thin material. Now why does it need to be thin? This is like totally just awful. Why do you think a target source needs to be thin?
I could see it be like cost of material, because when Professor Kearns was talking about it, she was like, you burn through a lot of those communion wafers doing this target.
Mm-hmm. Yes. So you're gonna burn through them, but you also wanna, why do I keep going through that raggedy eraser? When you are doing or making, when you're making material through a particle accelerator or through a cyclotron, and you have a thick source, you have like your charged particles, so we'll just say a proton. A proton, as it interacts with matter or an alpha particle, let's say, so we have a proton or an alpha particle, right? It will only travel so far into your material, right? It will only travel so far, okay? So if I have a really thick target, the only material that I'm going to transmute or make into whatever it is that I'm trying to make is just this section. now I've wasted this whole part of the target and I haven't made my material, okay? So you normally want a thin target so that you are completely utilizing the full target to make your material, okay? So what happens with this material, you normally dissolve it up and do something with it, run it on a column, whatever. But that's why you want to have like a thin target material. If it's like a a liquid or gas, you're not really worried as much with the thickness. Obviously, you don't want to have like a really long, huge liquid target because again, it's only going to travel so far. But in a liquid target, you have, as it's heated up, you have this, it creates a mixing where the temperature, it starts boiling, it'll make steam or a vapor, which will then condense along the sides and then drip back down into the bottom. So there's a sort of mixing going on. So when you have a liquid target, you're not really worried that much about the thickness because there's some, I don't want to say innate, but there's mixing that will happen inside of a liquid target because it's when it heats up, it creates that vapor and it creates that natural, yeah, there you go, yeah. So that's what that does. And then gases, obviously, they're less dense than solids. And so if you're irradiating a gas target, you're not really worried about the thickness of your gas target. You just want to make sure that your gas target is normally very well sealed because the radioactive gases that you are creating have a large probability of escaping if your target is not like leak tight.
So hypothetically, if we know the like MeV of the charged particle flying out of the cyclotron, we can calculate, because you also have to have a holder for the I call them little communion wafers because they're thin.
Yeah.
But you have to have like shielding for it, and then you also have to have it. You can calculate like, okay, with this much shielding, we need this much material.
Yes.
Okay.
So that's another way that you can. Okay. So let's say you have a cyclotron and it can only produce 10 keV protons, right? However, in order for your reaction on your target to make the amount of material you need your protons at 6 keV, right? So what we can do is we can determine, we can use what equation? This equation, right? So if we want to know how thick of a material that we need in order to reduce our intensity or our energy down to a certain keV, we would use this and solve for thickness of whatever property of material that we have. So if it's aluminum, we're going to use the mass attenuation coefficient, okay? So how much of this material will attenuate those protons, those gammas, whatever, by a certain amount, and that's the thickness of the absorber that we would use, okay? So if I started with like 10 keV protons, whoops. If I started with 10 keV here, and I need to get to 6 keV, and I have e to the minus mu sub mx, and I'm using plastic. As long as I have this mu sub n equals, what is that? Natural log of 2 over, wait, let me think. Yeah, so you'll have to have the mu sub m equals natural log of 2 over, is it the density? Lambda? No, it's not lambda. That's the decay constant. I'll look that up. I think it's the density. Mass attenuation coefficient. Give me a second, we only have like If you find it before me, please correct me.
Well, for half value layer, it's,
Yeah, it's
natural luxury, half value layer. But for the first one, it just says, inverse centimeters.
oh, it's over X. Where'd my marker go? Oh, here we go. So, let's see. Yeah, it is over, okay. So if you're using the mass attenuation coefficient, it's a function of your material, right? So you have to know the density, and usually a mass attenuation coefficient is given in centimeters squared per gram. So you have to have your density, which is grams per cubic centimeter, and you have to know the thickness of your material, which is usually in centimeters. So you take, wait a minute. Okay, let me get this right. Y'all, let's say it happens. Because this is not explaining it the way I want to. Divide linear to coefficient by the mass density. Yeah, that's what, okay, that's what I need to do. That's what I was trying to do. Divide by the density, okay, yeah. So you take your take your linear attenuation coefficient and you divide it by your density to get your mass attenuation coefficient. So basically, this right here is going to be centimeters squared per gram times oh, no it's not. It's gonna be given in inverse centimeters. And this is gonna be given in centimeters. So that should cancel out. I'm pretty sure I confused y'all. Nope, where did she go?
I think she went to the restroom.
Oh, okay, I didn't notice that. All right,
You
so,
confused her so much.
yeah. Sorry, that was confusing. Hopefully that follows. So this is inverse centimeters and this is grams per cubic centimeter. So this is given in centimeters squared per gram. So if you're given that value, just know that that means your linear attenuation coefficient is divided by a property of the material, which is your density, okay? So if we are looking at our cyclotron here, or our accelerator friend, and we wanna know like how much what thickness of plastic, lead, tungsten do I need to reduce my energy from 10 keV to 6 keV, then I would use this equation to figure out my X, okay? To figure out like what thickness of lead, tungsten, plastic, whatever, in order to get that reduction in my reaction. So the 6 keV is what I need in order to make my reaction go forward. Could I still use my 10 keV protons without the tungsten? Sure, I could, but I'd probably burn my target up and not make my reaction. You supply too much energy to a reaction, then you're not going to get the product that you desire. You're gonna get something else, okay? Or you're just gonna burn through your target. Like literally, not catch it on fire, but you're gonna turn it into something that's not useful.
Because you showed the scorch marks of them.
Yeah, so yeah, you can burn your target up if you have even if you have the correct energy and you irradiate it for too long, you can also burn it up. So you have to know how long you can leave it in there to make the desired amount. And that goes back into the equation that I erased where we're looking at yield, okay? So that N sub B equal to your flux, your cross-section, and for positively charged particles, the cross-sections look different than a neutron cross-section. So remember what a neutron cross-section looks like, and this is where we'll probably end. So neutron cross-sections is given like this. You have your cross-section given in barns, or you know, units for barns. And then you get your energy in MeV for your neutron. So the lower your neutron energy, the higher your cross section would be. So higher cross sections are good because the probability for interaction is high. All right, so then you get to this intermediate range here. This is your resonance capture, and this is your 1/V region. So ideally, you want your energy to be in a high cross-sectional area. If it is for a charged particle, they look a little different. They don't look exactly like this, but we don't go over that. But they use the same kind of concept for charged particles. They look and see where the cross-section for that charged particle is going to be high, and they choose that energy. And that energy, they determine how long can I radiate that thing for. And using this equation, you can determine like how thick of a material do I need in order to reduce that energy to whatever it is that I need. So it's kind of like fine tuning it. So you can insert like little filters, what they call them. They call them filters to create the exact energy that you need for your target for the reaction that you're looking for. So cyclotrons and accelerators are really good for making small amounts of material. If you're looking to make like Curie amounts and large amounts of material, usually you will put it in a reactor, okay? And you want to produce in good yield, okay? So if you want to produce in bad yield, you use like one of these down here. So, you know, I don't know of anybody that wants to not make anything in good yield. Decay chains, thorium, actinium, uranium decay series, knowing what nuclide belongs to what and how to determine that, and what they decay to, like what is their, what do they decay to in terms of a stable isotope, okay? And I think that, oh no, I got more. There's probably a couple more. So apparently we have class this Tuesday. So yes.
How do we go about determining which decay chain it came from?
Okay, so if we want to, let me see if I can pull up the lecture really quick. Do I have time? I got 4 minutes. If I don't find it now, well, we can save that for Tuesday.
Yay.
Yeah, I'll save it for Tuesday. So let me write that down.
Tuesday.
So what are we doing on Tuesday?
Next Thursday?
Because we have class Tuesday and Thursday.
We could do more review, or we can go over old homework.
I think work on internship stuff.
Or,
Yeah,
yeah, that, I
or
think
like
that's, did I say that?
working
Yeah,
on
or we can work on
projects.
our internship applications.
That's what I want to do.
Did you finish your resume?
Me?
Yeah,
Yeah?
okay. Did you send it to me?
No,
Your
you
updated
looked
one?
over it and, oh, was I supposed to send it to you again?
Yeah, well, no,
Oh.
I mean, if you want to.
I will.
Okay.
I will.
And I think I've looked over a couple other people's resumes, but I really would like for you all to apply before the semester ends, because once the semester ends, you might forget about it, and then you'll miss the deadline for the summer.
I will not forget.
And then it's a good idea to kind of have in mind like what type of